everybody to the GIMI Think Tank. As you know, every week we run this GIMI Think Tank platform. It's a pleasure for us at GIMI to see familiar faces, new faces, basically who are coming here to learn more about innovation, cutting edge trends, innovation, insights or GIMI programs around the world and how these GIMI programs are doing. And we hear about the state of innovation of a country and really cool things which are happening around the world. First of all, today we have a great speaker. I just want to do an announcement before. Today is a bit different, so we will have 1 hour of the GIMI Think Tank as we always have. Today is positioned on green hydrogen. As you know, we have a futuristic center on green hydrogen, and we'll always share insights about that. This is spearheaded by Carolina, and Carolina will run that meeting with our honor speaker today, Claudia Massei. After that, from 10 to 11, who wants to stay, please stay. We will run a meeting with the members of GIMI and potential members where we'll talk about the benefits of the membership in GIMI, and we will have a Q&A session. So let me start first with the GIMI video because always there are new people joining. So it's good for you to know who we are, and then I'll leave the floor to Carolina to present the speaker.
Hello, my name is Hitendra Patel. I'm the Managing Director of the Global Innovation Management Institute. I'd like to welcome you and join our vision and our mission of the Institute. Our vision is to democratize innovation everywhere, in organizations like universities or corporations, in high schools, in governments. And the idea is to unleash that creativity across the globe. Our mission is much more simpler: to train 1 million people worldwide, certify them, and unleash their creativity and their problem-solving skills to target any problem on this planet. The Global Innovation Management Institute has got certifications for individuals, for corporations, as well as for the government. And the whole idea over here is through certifications, people have the right to practice innovation. Through certifications, we create a roadmap for how to get better and improve as we get level 1 certificate to level 2 to level 3. We are today working with the Dubai government, the Qatar government, across Colombia, in Brazil, in the United States, helping these institutes and these countries become better in terms of their innovation journeys. We're working with corporations, giving them roadmaps, how they can go from level 1 to level 2. And we're giving certificates to individuals as they go from level 1, 2, 3, and 4 in terms of how they can actually innovate themselves, how they can innovate in teams, and how they can innovate in a company.
We've worked with several innovation consultancies, and we found the GIMI methodology to be able to help us democratize innovation very quickly across large groups of people.
Curriculum isn't enough anymore. We need to really be finding ways to expand the school into the community and bring the communities into the school. And design thinking and the GIMI impact model is what's going to help do that. I think that we really need to start looking for authentic, experiential learning opportunities for our students. And this is a really great framework that teachers can use that makes it easy to do.
The value that we see being part of the GIMI program is that we can offer capability building for students, for professionals, for corporations, and that's really exciting to be able to create a language that can help everybody connect with what strategic innovation is.
Today we've got 25 countries who are partners of the Global Innovation Management Institute. We'd like to see all 195 plus countries becoming part of this institute. So we are looking for training partners across the globe. We're looking for university partners in every one of those countries so they can be part of our network. And we would like to see companies and corporations around the world all embracing the certification programs of GIMI. And as a result, we can target any problem and we can solve any problem. Join us on our mission through certificates to give people the right to practice and a roadmap of how to improve.
Okay, thank you for that. Carolina?
Okay, thank you very much, Adila, and thank you to the Global Innovation Management Institute for this invitation. We are always looking for ways on how to share knowledge about different industries. So we are hosting right now the Energy Transition Network. So hopefully this is going to be very insightful for you. So let me just give a quick introduction of our amazing speaker that we have today. 1 second. Okay. So she is Claudia Massei. We already have her with us in this session. So she is the former CEO at Siemens in Oman. She's going to talk a little bit about digital transformation and energy efficiency. So Claudia was this CEO at Siemens, and she was focused on transforming pretty much the culture of the organization to be more collaborative and to co-create also with different, let's say, levels of the company. In her role as CEO, she was driving pretty much the digital transformation, innovation, and energy transition. She was overseeing as well different projects in microgrid automation, predictive maintenance, energy efficiency, and remote commissioning. She also has experience on different sectors, including power generation and distribution, smart grid and digital solutions, and industrial applications. So Claudia holds an MBA from the Wharton School and an aeronautical engineering degree from the Instituto Tecnológico de Aeronáutica. And she also has done some executive education programs at Stanford, Princeton, Cambridge, Oxford, and London School of Economics. So we are very excited to have her here. Claudia, thank you very much for joining us. And I'll give you the floor now for you to inspire us on this digital transformation and energy efficiency theme. So thank you very much, Claudia.
Sorry. It's my great pleasure, Carolina. Thank you for inviting me. And I'm going to share my screen because I do have a presentation to share. Just let me know once you are. Can you see that?
Yeah,
we can see it.
Perfect. So again, it's a great pleasure to be here today. And I would like to, without further ado, I would like to talk about first digital transformation, how that is impacting like both infrastructure and industry, as well as with a specific focus on energy efficiency. Basically, if we look at all the changes that we have been going through, if we apply the technology that we have available today, we can realize up to 50% material savings in the industry, in the manufacturing environment. And if we look at the infrastructure in the buildings, we can get up to 30% of energy savings, right? And I'm gonna like basically elaborate a little bit more in this presentation on what are some of the technologies that are on the edge right now that are actually being responsible for these two types of achievements, and then open up for questions later on. So starting first with industry. Like here we're talking about not only like in the production side, like during the operations of a production site, but also in the construction of a production site. And that's the example I'd like to start with. How can we use, for example, the technology of a digital twin? That is something that we talk a lot about in the whole hardware industry. We talk about using digital twins. And here's an example of how can a digital twins help to save materials during the construction of a manufacturing facility. Here I have for you, it's a video of of a Siemens digital twin of a greenfield factory. It's our Nanjing factory for the electronics that we produce. Basically, what we have done is that we made a digital twin of the site before construction, right? So here you have some scenes of the site after construction merged with the like basically rendered digital twin that we have produced before construction. The interesting thing is that even after the plant starts operation, you keep the digital twin running because you keep this iterative process where you get data from the real operation and you feed back into the digital model so that you can compare the prediction of the results with the actual results achieved. And basically you can this way like optimize your digital twin as you go, right? So in this case, we use the digital twin to three main things. We evaluated lots of different concepts of layout for the factory so that we could optimize the results. And this means, for example, if you want to have an L-shaped production line, a U-shaped, W-shaped, or just a straight line. And then you can like see how people interact differently, how the materials go through differently, and how you can pretty much like test the outputs of each type of configuration and choose the one that suits your goals best. We also had a simulation of the production flow. So optimize the layout and simulated the flow of itself so that you can also maybe change some sort of even like how many people you need to hire, for example. You may need to change the number of people that you thought you needed to have, because the layout may also impact that. Maybe you can get to a faster layout having even less people, for instance. So here, some of the results that we achieved with that was, for example, we built this production facility, as you can see, during the pandemic. And even though we were in the pandemic, we ended up arriving at less than 1% of non-conformance costs, like divided by the total of the construction cost, right? So 1% of the construction costs as NCCs is actually like, even without a pandemic, would already be a great achievement, with all the complications that we had during the pandemic with, especially in China, right? Because this plant is in Nanjing. This is actually a very great result that we could achieve. Moreover, talking about all the simulations that we have run, we managed to save 40% of the space, because actually we moved an existing production site to this new greenfield factory that we built. So if we compare the original site with the factory that we built, we have 40% less space needed to have actually 30% more volume flexibility. So this means like changing the products that we're making in the production lines, and how fast we can switch from one product to another, and also 20% more productivity. We also managed to get 50% faster restocking capabilities in this case, and we also managed to reduce the emissions of CO2 by 3,300 tons per year of less emissions, and all of this led us to a LEED Gold certificate for the factory. Well, this is a Siemens example, but if I need to give you like also an outside of Siemens example, I cannot disclose the company name, but there is a vaccine production company in Brazil that is also using this technology of digital twin, and this was obviously like in the context of the COVID vaccine was very meaningful. They managed to get 4 times more vaccines, so like it went from 150 million to 600 million per year. Then also much more efficiency in general in the plant. Also the ability of even to switch to this 4 times more vaccines, it's a much more agile compared to other factories, and therefore you can accelerate the time to market of a product that you may be producing, right? So this is pretty much what we have achieved in a real case example outside of Siemens. But here, if you start thinking about this, you say like, look, there is a lot of technology here in building the factory. What about in the day-to-day of the factory? And that's where I come to an example that I'm going to talk about, the robotic grasping. So what you see there, it's a combination of machine vision plus edge computing. And I'll elaborate a little bit more on each of those. The context here is the following. We have nowadays about half of the people that work in a manufacturing site work with picking. So picking means pretty much you take ready-made parts from a machine, and then you simply put in a basket so that it can be gone to another line or like to the delivery part of the warehouse or whatever. And half of the people normally work in such functions. and it is a very boring, tedious function. These people could probably be a lot more challenged if they would be working on something a little bit more stimulating. And there is another problem. Even if you're going to say like, no, maybe they like to do that, the data shows us that they probably don't, because as of today, there are 500,000 openings in the US alone for such jobs in factories. So there is a clear data, clear evidence that people are not necessarily super interested in this type of jobs anymore. And how can we then improve or basically use technology to replace these people? And in a way that is, let's say, failure proof, right? So here you see an example of a robotic arm, pretty much equipped with machine vision, as I mentioned, and they are pretty much just moving things from one side to another. And you may say, like, look, and by the way, the edge computing topic is because if you put the processor at the edge, which means like very close to the machine itself, and not on a cloud, not on a centralized server, you just have much more energy efficiency. So you save energy by doing all the processing for this technology to work at the edge. Then you may say, like, look, but I have seen these robotic arms since I was a child. Like, it's been around for 40, 50 years already. Why is this so relevant right now? And the point is the following here. We have actually, one thing is if you say, okay, the machine will pick one part that comes in this shape and format and exactly in this position, and it's going to move to that exact other position. But here, what we're talking about is a lot more, a form of grasping that is a lot more intelligent. It is actually, because of the computer vision, you can train, and in our case, in our factory, we actually have trained this arm with 23,000 different configurations, varying from different movements, from taking from different positions and putting in other positions, and also from different shapes of objects. So these 23,000 data sets have been used to do some sort of artificial intelligence, if we may say, so that this robotic arm is able to identify the shape, whatever shape it comes. It is able to position itself in the best way to pick it and pretty much take the part to a location that you may simply decide as you go, right? So you do not have to reprogram the whole thing over and over again. And that is exactly the novelty about this, is because it is a much more intelligent grasping. And now I'll touch a little bit on something that is not so much technology, but I think is a question that comes so often that I feel the urge to address it here, because you may say, what about the people who are doing these jobs? Like, they're going to actually lose their jobs, and that's the solution that we have, because, as I mentioned, we have been adopting such things in our factories, and not only this technology, but also, for instance, predictive maintenance that eliminates, in theory, the need for a machine to be fixed, right? Because you're going to be doing the maintenance before it fails, and therefore a lot of the technicians are no longer needed. So what is the impact to these people? And this is one thing that we have at Siemens, we have been working on. We have a program called Next Work, and this program is actually focusing both on blue collars and white collars. And I'm going to address both of them. And basically here, for the blue collars, here's just an example. We have, in one of our factories, we're training people to go from mechanic technician, so the guy who would go and fix a machine when it fails or when it's down, to a maintenance engineer. As I mentioned, there is a predictive maintenance need, because when we use the technology for predictive maintenance, the technology will tell us what will fail when, most likely, and then you want to do maintenance before it fails. So you need those maintenance engineers. And then you also need, of course, like the person to be skilled from fixing something to avoiding that something actually breaks down. And this the skills are a little bit different. As of end of 2022, we had already 40% of our blue collar workers already trained in this. And the goal is actually to finish by next year, because otherwise these people would probably run out of their jobs by next year. And that's the same thing as when we go to the white collar space. We had like pretty much a lot of people just doing paperwork. And these people actually, they need to do like paperwork as in like filling out forms of like when a machine failed, what you have to order and this and that. Like, so lots of things that are being automated by several types of systems. And here the point is mostly about having engineers and like transforming these people with some of the capabilities of engineers and technicians so that they are able actually to work along the technology in, for example, predictive maintenance, right? So we actually identified 23 new roles and we're training people like in order so that they will not lose their job, in order for them to be upskilled and be able to keep their jobs and keep giving good results to the company. But like now, if you tell me like, okay, but you said already like this, the whole AI is something that has already been talked about for some time. It's not like something so new. So what is the next frontier of disruption? And to me, it is the connection of large language models such as ChatGPT to the industrial environment. And here we're talking about, for example, having a SCADA digital companion. So think of ChatGPT, but to help a technician who goes troubleshoot a SCADA system. And that would be like basically a sort of like encyclopedia that would accompany the person while they go to the site and help them with a kind of like a troubleshoot manual. We also can think about code generation to program robots. So we're just talking about the robotic arm. Nowadays, we need actually to have like someone coding and like train, like even if you go through the training routine for this model, you need a lot of coders. In the future, and I think this is even now a reality already, that you can simply describe what you want as a code or what type of movement you want your arm to do, and with the words that you describe, the software can code by itself. So how do you need to pretty much prepare this code so that the robot can move the way the operator said it should move, right? So you just like need the words and no longer the coding capabilities. Same thing about predictive maintenance. You can also use such a large language model to actually keep track of all history of failures of several machines. And whenever there is a new failure that comes up, you can analyze the history with the data that you need. So basically this type of technology can tell you like what are actually the variables you should be looking at. And through those variables, it can actually tell you what is the most likely reason for the failure, much better probably than a technician could. And finally, the dashboard layout definition, because in a factory environment, you need to have, like normally you have like screens beside the machines, and you need to have this dashboards like in the most user-friendly way possible, so that your technicians can react more quickly to the information that's coming through. At the same time, you may have like for the management level, you may need to have a different type of layout, and the large language model can actually, based on what you tell about the job profile, it can actually figure out by itself what's the most relevant information that it should be displayed, and as well what is the most, let's say, natural design for this display as well. So those are some sorts of some types of large language models use cases that are being used in factories or are being tested in factories nowadays. Now let's go to the infrastructure portion. That's where I'm going to address a lot more the energy efficiency topic, although there were some let's say benefits or advantages of the technology in the manufacturing side for energy efficiency as well. But in buildings, that's where energy efficiency becomes really like the main driver of recent technology that's being developed, because of all the whole sustainability concerns and climate change and so on. So here we're talking about, as I said, talking about saving up to 30% of the energy consumption in buildings. And this has a lot to do with cooling and heating many times, right? So here, let's talk about data centers, which are a type of building that really consumes a lot of energy and really needs a lot of cooling, because this is pretty much the if you don't have cooling in a data center, you simply don't have the capacity that you need to process all the data. And more and more, there's more and more need for data center cooling. Think about the hyperconnectivity of 5G. Think about also all the topic of the workforce that nowadays work in the data centers to repair, to optimize, and so on, to give maintenance in general. Like a third of this workforce is going to be retiring in the next decade, and that means you need actually to have probably a lot more work because the capacity is growing with less people, because you're not going to find people so fast, or you cannot count that you're going to find people so fast to replace these people who are going to retire. So the solution for that is actually simply to be able to have a lot of this cooling capacity optimized so that with the same chiller plants, you can actually achieve many more results. And as well, so that you can have maybe everything controlled from a central location. So that you diminish the need for people being like relocating from one plant to another, right? So one of the main issues of data center is actually the mix of legacy equipment. You have lots of different suppliers that provided things over the time. You have new equipment combined with old equipment because maybe something failed and you changed only partially the system. And this legacy actually makes it like the whole functioning of the system far away from like optimized or far away from most efficient. And many times actually you even end up providing more cooling than needed. So that is also one thing that we can actually address. And you address this with a technology called thermal optimization. Now here we're talking about two different things. We have a topic of like managing the temperature of the air that comes in, and as well the airflow, so the path of the air within the data center. And here's where something called the white space comes in very, very importantly. And I will explain what this means in a bit. So talking about, we're going to actually be, so thermal optimization means you look at everything from the cooling tower. That's where the air is cooled down, and that's where basically what determines the temperature that the air comes into the data center, as well as all the inlets and all the temperatures within every single corner of your data center. So basically, depending on how the air flows through the data center, you're gonna have some corners colder than others, and you need to make sure that the ones that really need to be colder are the coldest, and the ones that don't need are not. Another thing that makes the data center a little bit tricky is actually that it's quite unpredictable which part of the data center is going to be heating up more in a given moment, because it depends from which server is being more demanded with, has more load at a certain moment, right? So that's why you need some sort of artificial intelligence, because you need your whole system to react in real time to the changes. So if you have one unit like basically with a higher load and heating up more, you need to make sure the cold air comes there first to basically bring the temperature down. So talking about what can be done here, basically the first thing is about the temperature that the air comes in. And this is something that normally you have like water-cooled chiller plants. This means that the air is cooled with cold water that passes through the system. And many times this cold water passes way too fast. Like basically if you go into the physics of it, like the optimal heat exchange or heat transfer process happens when the temperature of the water leaving the system minus the temperature of the water entering. So the delta temperature that the water suffers within the system is 6.9 degrees Celsius. I'm sorry, I didn't convert to Fahrenheit, but basically this should be about like 14 Fahrenheit or something a little bit lower than that, 13 Fahrenheit probably. As you have this water, if the water comes in the system at let's say 50 Fahrenheit and leaves at 55, you're actually pumping way too much water. And you could be pumping water slower so that the heat exchange would happen a lot more within the amount of water that's passing through the system, and therefore you would save water and as well save the energy from the pumps that are pumping. right? And saving the energy as well that you need to cool the water down. So you, from all these combined savings in your system, you can achieve up to 30% of a saving. And this without compromising the temperature in the data center itself. The other topic that gets us to this 50% energy savings is the white space optimization. And that basically means where in the data center there's going to be more cool air being directed to. So you're looking at the fans. Maybe you don't need all the fans turned on at the same time. Maybe you have some part of your data center that is not even used because you have like too old equipment and you basically deactivated that, so you don't need to send air over there and so on. But basically you just need to have sensors throughout your data center, and then these sensors can actually the data from the sensors can be used in real time to control the fans that are directing the air through it. And this also reduces a lot the risk of failure of some of the servers, because you're going to ensure that they really stay at the temperature they should be staying. So this is one of the examples of energy efficiency. Of course, this can be used also for normal buildings, but data centers is where it's really very impactful because of the white space topic that gets us from 30% to 50% savings. Now talking about renewable energy. And here it's many people say that there is a problem with renewable energy because you cannot trust it. You cannot have like a system relying 100% on renewable energy. And we have Siemens has worked on a project in Hawaii that has proved that you can. Of course, like put this with a grain of salt, it is Hawaii, it is like a limited amount of energy demand and so on and so on. But nevertheless, we have a lot of tiny, let's say, centers, rural centers, or even tiny urban centers in the world that could be using such a technology. And here we're talking about having a digital twin of a microgrid, of the power grid, basically, but it is like, we could consider it to be a microgrid because the need of electricity there was basically didn't go over 5,000 megawatt. Basically, we started with a situation in which they had 200 megawatt of solar energy being produced, and basically, of course, there was a peaking consumption that couldn't necessarily, like, that needed to be, let's say, compensated by thermal power plants, because the solar plant could only provide for 65% of the time of this usage during peak times. So basically what we did was getting a digital twin and understanding what needed to be done in terms of batteries, in terms of maybe having some of the demand not being used at a certain time. So if you have, for example, some processing plants that could be operating in different times of the day, changing this and so on. But basically doing that with this digital twin, we managed of the grid, we managed to get to 65% of renewables during peak time to 100% of renewable during peak time. And also the possibility of scaling up from 200 megawatts to up to 5,000 megawatt of power. And this, of course, integrating, we're only talking about solar here, but you can also like think about how you integrate wind power to this as well, and so on. So this is another example of how can you do AI and digital twin in the infrastructure sector for you to save energy. And here it's not necessarily saving, but it's actually optimizing into renewable energy. And then lastly, there is also an example of digital vertical farms. And here it's also talking about efficiency, let's say, in energy somehow, like, but basically it's a lot of like land efficiency, water efficiency, but because in such vertical farmings, and this is actually very maybe not so relevant to bigger countries like Brazil or the US, although it could be, because then you could be producing very close to urban centers, right? You don't need to transport the groceries from far away, because like normally you have lots of land to produce groceries, but they're not like beside Boston or New York. They are pretty much far away from those centers. So you also have transportation costs and the energy that goes with this transportation as well, right? So how can you actually enable large-scale, sustainable vertical farms with a very low ecological footprint? Because, as I mentioned, like you actually have 95% less water being used here in comparison to a normal farm where you would be growing those vegetables. And you also can have a full intelligent energy system with power distribution and fire protection and safety and asset management, everything pretty much digitalized, running on a software that can optimize your energy consumption. In this case here, we're also talking about being able to integrate renewable energy to power all of this, which gets us to even more savings in terms, or at least even more benefits when we're talking about powered by renewable energy in comparison to traditional energy. And one last detail of this is that per square meter of land, you can produce up to 300 times more. First, because you're getting them to be growing like very close by one to the other, right? You're optimizing the water path, so you can pretty much get, and you also have the growth rate of these plants is much higher, simply because you change the lights, so you get a cyclical. You basically you simulate a day that is much shorter. You can simulate days of like 8 to 12 hours. Just by changing the light that they get, and they end up growing much faster. So thinking about like squeezing them in a much smaller surface, doing it vertically so that you have several floors of plantation, so to say, and at the same time you have all these plants growing much faster because you can play with the times of light that they get. You can produce up to 300 times more. So I'm coming to the end of my presentation here. And I just would like to leave you with the message that technology does drive sustainability. And the best way for you to have this being driven is actually getting the real and digital worlds interacting with one another, and basically having one feeding the information to the other one. So you have the digital world with all the simulations that you build, for example, in digital twins and so on, and then you build your real world based on that, and then you use the data from your real world to feed back into your digital model, so that you can, like, as you go, be re-optimizing this digital model and figure out what needs to be changed then in the real world because of this new data that you fed. So it's a continuous process. May sound like a never-ending thing, but nevertheless, it is pretty much how you can use the technology so that you have all the time the best and the most efficient processes in your buildings, in your plants, and so on. And here just some numbers that what we can achieve with that. If we're talking about decarbonization, we can get to 40% of carbon saving. If we're talking about energy efficiency, we can get up to 40% of energy saving. And if we're talking about material efficiency, we can get up to 50% of material saving. And I would like just to say thank you and open up to questions if you like.
Thank you very much, Claudia. Very insightful how technology and sustainability are pretty much creating these synergies to be able to deliver those results across Siemens and, of course, across multiple industries. So let me invite Ron Jonash, who is one of our thought leaders from the IXL and the Global Innovation Management Institute. He is going to help us also to drive a couple of questions that he has, and of course from the crowd. So Ron, do you want to open your microphone and then share some of the questions that you kind of have seen and that you are have?
My mic says it's open. Is it open?
Yeah,
okay.
We can hear you.
Great presentation, Claudia. Very impressive, and lots of good different examples of digital twins and how they combine to drive potential step function increases in improvements in sustainability and carbon and everything else. My question is, what do you see as both the breadth of present applications, but also the future? What's next, particularly in terms of simulating human behavior? So behavioral economics, purchase and use behavior, behavior of suppliers, behavior of customer groups. If we can find a way to take that pseudoscience and combine it with the very specific and well-developed engineering and technology science we have for digital twins, it would be magical in terms of applying this to, like the last example used, existing farms, as well as new vertical farms, to managing ecosystems where you have a wide variety of behaviors interacting with engineering systems. So what do you see as what's next, or what do you see as current applications that might incorporate a little more of behavioral economics and behavioral psychology?
Okay, so let me start by addressing your question from an example that doesn't go into maybe so much the intellectual behavior, but it goes into the human behavior. That is something that we do use when we talk about digital twins of manufacturing facilities. And this has to do with how you train your employees and how you deal with health and safety. So basically, one of the advantages of a digital twin is that by the time you finish the construction of the real factory in the real world, you can actually hit the ground running with your staff, because during the construction time, you can actually train them in a kind of a metaverse of some sorts, right? You can actually build your factory, like your digital twin that you already had, as a virtual reality. And in this virtual reality, you can actually train your people. And from the training times, you can actually also see their behavior, and you can actually already identify potential risks, like dangerous situations, health and safety concerns, and so on. So that is definitely one of the things that you can use. I mean, I don't know how much the metaverse is really going to stick. Obviously, I think it's no, for whoever follows NVIDIA and Siemens, we have actually a partnership to address the industrial metaverse, which is exactly like basically building this environments for people to have like factories that work in a virtual world. So we believe that as a company, we believe that this is the future. This is really going to take off. I know metaverse is a very polemic or controversial topic. Many people don't believe necessarily in that. Siemens believes in it. And we have been addressing that, and there you can address a lot of the behavior topics when it's talking about how people really behave as like physically. Then comes like the whole topic of let's say behavior economics, and that is something that I also believe you can address with large language models. So let's put, for instance, if you're talking about procurement, you may get some sort of like from the whole psychology, you may get someone to decide, oh, I think this is a great offer from this particular supplier, and decide to sign a contract with a long-term agreement, for instance. And maybe that was not the best choice. And I think if you have actually some sort of like large language model, ChatGPT or another one, that is able to analyze the data and actually help you make that decision much more in an analytical way, because a lot of the decisions that we make are simply from feeling or from a recent memory, and or even like the relationship that you have with the person may play a role, and so on. So if you're able to actually avoid this this type of reaction by using the data that a large language model can have to analyze, I think that's pretty much what's going to be happening in the future. Same thing with the legal departments that are able to analyze contracts and tell you like, okay, this clause here may get you in trouble because of this past event, and so on. So I think these are definitely like fields of applications where we're going to be seeing a lot more data being used to make decisions.
And I think one of the implications, hopefully, that everybody is seeing, or at least that I see from what you said, is that these digital twins and simulation models should be built to last. They have incredible applications after you've built your factory, after you've kind of retrofitted a factory, for training, for lots of other things, for selling, marketing, lots of other things. And so the investment that you might see is somewhat daunting at the front end pays off in multiple applications that reduce energy costs, material costs, as Claudia said. And I think that was an incredibly compelling presentation of that. So let me open it up to other people now who have questions. So Carolina or Rila, you may want to call on others since you have the chat box open.
Sure. So I think the other question, Claudia, that people was kind of sharing on the chat, that I think you mentioned already, that you were kind of answering her right now with Ron's question, but is it the way that you see, for example, this technology and sustainability playing with people, right? Because that's one of the concerns that probably some of the leaders of different industries have. Like, how do you see this equation when you add the talent component into the picture of, because you mentioned also of, let's say, is it a matter of upskilling these people? Is it a matter of finding new capabilities for the people to be able to manage and to pretty much like work synergistically with the technology to be able to deliver those results? How do you see kind of these people or staff or collaborators into a company playing in the role in this equation?
Mm-hmm. So first, there is like the example I gave from the factory standpoint, right? Like, so talking about getting blue collar workers that were technicians and making them like able to perform some engineering tasks, right? I'm not saying you can make a technician into an engineering with a 2-year training, but you can get them trained as engineers in very specific things that they can be like pretty much adding value to the company later on. There's also the topic of white collars in a factory environment where you have like the paperwork topic and so on. And finally, there is definitely also the whole point of professions that are coming up, like data scientists or prompt engineers, right? I think prompt engineer is one of the latest one, and that is simply like knowing how to ask questions to search a large language model, right? Because it's a little bit like when Google came up and it's like, okay, how can you conduct a good Google search? And nowadays is how can you get the most out of ChatGPT? How can you avoid hallucinations? How can you also have the critical sense so that you figure out there is an hallucination very upfront, and you decide like to double check that answer, like which questions, which answers should you be double checking, which shouldn't you, and so on and so on. So I think there is definitely like a lot of need for people to start upskilling themselves into this. I mean, of course, if you only use, let's say you're in the legal department and you're going to use a large language model to help you analyze a contract, that's one thing. Another thing is if you're hired only to use large language models. But I believe like these people who are going to start to use large language models as an extra tool that they have among so many others that they already use, these people need to start understanding what are the pitfalls, what are all the options out there, because ChatGPT is one, but then you have also the APIs that link to it, and you have also other companies coming up. I mean, Google has its own solution as well. So it's basically like understanding what are the pros and cons of each solution. And another day I was watching a webinar about this, about prompt engineering, and it's really depending on which model you're using, you may need to ask questions in a different way. And even within ChatGPT, this happens. Like some people say that like once you go from 3.5 to 4, if you ask the same question, you get different answers. So it's really like about knowing how to ask those questions, because at the end of the day, I think this is still very unclear for now. But as of today, you as the employee, you're still liable for whatever answer you provide, even if you say, oh, it was ChatGPT that told me that. But if someone loses the job, it's going to be you, not ChatGPT, right? This may change in the future. They may find a way to blame ChatGPT in the future, but this is actually one of the main points. Is actually nowadays finding an answer is no longer a problem. The problem, which I think is a much more complex one, is actually how can you ensure that this answer is valid, is bulletproof.
Thank you very much, Claudia. Yes, we have been hearing also that probably what's going to happen is that you need workforce that has like deep knowledge on some specific tasks, as you were mentioning, but they have this transversal also knowledge to be able to apply, like in terms of technology, to be able to, let's say, use and leverage technology. Because at the end, as you're saying, we are the ones who are going to be deciding which information to use and which information is not going to be, let's say, useful for whatever task we are doing. So thank you very much for that. So I don't know if there is any other question. I don't see more questions here. Ron, do you have any other comment, or should we leave the floor to Claudia for some last comments? You are on mute.
I didn't know I was unmuted.
Okay.
I guess, Claudia, I don't know if you can comment from this because it's not kind of Siemens kind of target market, but I think many of the people on this call, many of our ambassadors in different countries, developing countries, et cetera, see this as a bridge too far or something that's in the long distance. And I wondered if you could comment on how normal people can bring this down to earth and potentially find easy applications of digital twins and simulation, even if we make up the personas, even if we kind of hypothesize on how the engineering systems work, just as a tool that they should start getting used to, because it is, in your view, our view, I think everybody's going to take the world by storm. And so how do we get in our mission as GIMI to democratize innovation? We want to make these digital tools something that large numbers of people can see immediate value and applications of with their clients or in their companies or in their universities. So I wondered if you could comment on practical, near-term, low-cost applications and ways to learn about how to use digital twins, example, or simulations.
Yeah, no, absolutely. I think so. First of all, that's also why I chose the example from like the client example from Brazil. I mean, I think some people put Brazil in different buckets, but I think originally being from Brazil, I can say I think it is pretty much a developing country in so many ways, and I think that is actually an example of like a case that basically the client decided it was worth going through the cost of having a digital twin for the facility, because it would pay off in terms of the output that they could get. Of course, COVID made it like an easier case as well, right? Because it's if you can produce vaccines locally, and then compared to the huge need that it was at the time, and the fact that otherwise we would need to import it, and there was no time to lose. So that definitely made it a little bit easier to argue for this case. But there are also some, I mean, I cannot like say, yeah, the whole developing world is going for digital twins as of today, but there's definitely like so many cases. I think like the main point is if you look at companies that really need to manufacture something, like for instance, even in our case that we got our factory in China to be using this technology and not a factory in Germany. Our first digital native factory, which means being born from a digital twin and not doing a digital twin of an existing facility, but something that you first design in the virtual world to then build in the real world according to that model. Our first digital native factory is the one I showed to you in Nanjing, and China, you can also argue that is not necessarily a developed country already. I think in the manufacturing space, it depends also a lot on the output that you get from the manufacturing facilities for you to make ends meet, right? So if you're thinking about Indonesia has huge factories, you have Vietnam as well. So you can definitely like get the economics to work out in those places because they're like huge manufacturing the capacity for that. If you're thinking about Africa, for example, I would say maybe not a digital twin, but you can definitely argue for a microgrid, right? So for example, the example I gave from Hawaii, it was a digital twin of the grid system, but it was as well, before getting to the digital twin stage, it was a microgrid. And then later you can also have software that optimizes the microgrid, which is not as fancy or expensive as a digital twin, but can also help you to optimize your resources and save some sort of energy. And this is like definitely a solution that we have applied in Chile, for example, in the islands. It's a very good thing for islands in general, or for villages, or for like places where you don't necessarily have like you try to get like a place where the peak is not so huge, so that you can actually try to manage everything with batteries and a combination of solar and wind. But that's definitely, if you get a microgrid with an optimization software, I think it's not a digital twin, but it is a fancier solution than what they probably have nowadays. And that is also very much feasible in many countries. Of course, I mean, Africa will not have so many examples, because for sure Siemens is definitely not a company focusing on the African markets. But if I look at Latin America, we do have a few examples of microgrids, for instance.
Claudia and Ron, thank you very much for these thoughts. Claudia, just any last thoughts that you want to wrap up before we pretty much start the next meeting that they have with the Global Innovation Management Institute? Any last thoughts from your side to conclude your...
Yeah, I mean, just thank you again. And I was very happy to see one comment like talking about the good presentation on tech and sustainability, because definitely sustainability, although it was not on the title of the talk, it is a topic that I'm very passionate about, and I'm very happy that the message of sustainability is sticked here today.